Okay, with a little luck, I believe I'm now live. And I just need to switch the camera so it actually shows me and not my paper. Uh, Great. I think everything's working. Um, yes. Okay. I can see myself on the stream. We're in business. So hello, welcome everybody who's tuning in to my pilot episode of PhD Live, um, which is my attempt to both document my PhD in particle physics through the video format, but also to sort of help people tune in to what being in a PhD program is really like, because I'm just starting and I don't know what it's going to be like yet. But I know that when I was an undergrad a couple of years back, it would have been pretty helpful to get this kind of firsthand exposure and the ability to ask questions, um, not just to real PhD students, because you can find lots of real PhD students, but to sort of to see them at work. And I'm hoping through this platform that I'll be able to really demonstrate the process and the progress that happen uh, throughout the course of a research project. Um, I see I see that we already have some comments in the comment section. Someone's named Logan Boyd says, "How long did you know physics?" Well, that's a great question, Logan. Um, and I think the answer is I still don't know physics, but I'm working on it, and that's definitely one of the main goals of the PhD is to is to is to know physics by the end of it. Um, no, but in all seriousness, I think that the main there's sort of three main goals I have for this streaming project, or sort of maybe three different types of audience members that I'm envisioning. So one, like I already said, I think I could see undergrad students or master's students who are thinking about doing a PhD watching this, and hopefully asking questions. And I'm definitely planning to do a lot of sessions where people can ask questions, like ask me anything, and I'll try to answer as honestly as possible about what it's like to be a PhD student, but also um, the maybe the steps that I think were important in getting me to this stage. Um, and then I think the second category could potentially be um, people in other areas of science that maybe want to learn about particle physics, high energy physics in particular, and also machine learning, which is sort of the other facet of the project I'm going to be doing. Um, so if anyone tuning in is in that category, I'm definitely planning to do a lot of sessions where I go into more technical detail about the things I'm working on. I'll try to do sort of the video equivalent of um, paper reviews as I read different research papers, and as I work through some different textbooks, kind of um, trying to teach different topics as I learn them, which in my experience, is definitely one of the best ways of making sure that I learned something, is to try to explain it to somebody else. And those will definitely be interactive sessions as well. And then the third category, I hope that some people watching might not be scientists or science students, but just uh, members of the general public who have an interest in these topics, because they're important topics and they impact everyone. Um, so I hope that if you're tuning in and you don't have a science background, um, this will still be accessible to you. And I know that particle physics has a reputation for being difficult and not easily understandable to people who don't work in that area. Um, even within science, people sometimes think that, and I definitely want to change that stigma, because I think that even though it has some definitely very cryptic and technical parts, um, a lot of it can be explained in a way that you don't need to have a PhD or any kind of degree in a science field to understand. Like this is stuff that everybody should be able to engage with, and that's definitely something I'm pretty passionate about. So that's my quick summary. As far as the actual formatting of this stream, just to give a quick sort of guided tour around the layout I have here, just in case anyone has any suggestions, actually, because this is my first live stream. Well, I did a test one about a half an hour ago, but this is my first actual live stream. So I have front-facing camera going on. I'm envisioning maybe shrinking that a little bit if I'm working on something on the right side of the screen here. Also, if anyone knows how to make my cursor show up, that'd be cool. Oh wait, no, it does show up on the right side here. That's perfect. And here on the right side, this will be where I put papers that I'm working on, or reading, I guess. Well, eventually working on code that I'm writing, code that I'm debugging. This will sort of be my active area where I show off what I'm working on, and then I also I'm very excited because I figured out I got some software that allows me to switch between cameras. So here we have my downward facing paper cam. It's been pointed out that this is kind of blurry, but I'm hoping that if I write at a double font size, that it'll be at least mildly readable. And yeah, that's pretty readable. So for now, I'm just going to stick with double font size, and I won't be writing on paper all that much anyway. This will more be for diagrams if I'm trying to illustrate some point. And if anyone wants to donate some kind of super fancy webcam that can read like my tiny handwriting scrawl, that'd be great too. Let's see, comments coming in. We have Charles McKee, shooting particles at near liminal speeds and watching what happens when they slam into other objects. Laser guns. Yes, that does pretty much sum up the experimental side of what I'm doing. Oh, he also points out that I need a second light source, which is definitely true. But at least the head shadow is only on the left side of the page right now. Yeah, so this is probably a good opportunity to actually talk about my project. So to give a little more information about myself, my background is primarily in physics, but I've done some wider study beyond that. I've done some research projects that fall into the electrical engineering category. Definitely most of my undergrad was very application heavy. My interests are much more on the theoretical side of physics now, the mathematical side of physics. But one nice thing about, I think, physics research and even particle physics research in particular is that the experimental and the theoretical and the engineering sides really have to work very close together or nothing gets done. And so talking about my project in particular, I think will definitely demonstrate that. So let's see, how can I diagram this out efficiently? To give a quick overview of the state of particle physics, when I say particle physics, what I'm really talking about are the fundamental particles. Actually, I'm just going to switch this back to front-facing camera. Yeah, I don't need any diagrams yet. What I'm really talking about are the smallest particles that we can think of in the universe. And as science evolves, this always changes. For the ancient Greeks, who were just barely starting to conceive atoms, for them, particle physics would mean maybe a grain of sand would be thought of as kind of an indivisible thing. And as time has gone on, we came to understand about atoms and about the nuclei that are within atoms and electrons and smaller particles within these, and the layers just keep going down. So, unfortunately, particle physics is not well defined because there will probably never be a truly smallest scale of physics. Like it certainly seems that we're just going to keep uncovering more and more levels of complexity in the universe, and sometimes that's just the way science is. But the state of the field right now, and the state of physics, particle physics for the past about 50 years, has been one very successful, very thorough model, which we fittingly call the standard model of particle physics. Um, so I could draw sort of. I'm not going to because I probably get it wrong. Yeah, maybe I can get it. I'll guess, and we'll see how close we get. Um, Particle physics, we can write down sort of a periodic table of the types of particles that we know about right now that make up all other things. So one category of particles are the quarks, and I think of the fundamental particles that we know right now, these are probably the most well known because they make up protons and neutrons, and they have a snazzy name. Quarks is memorable. One exciting thing I learned since I moved to the UK is that there's actually a type of food called quark. I'm not sure if anyone knows if it predates the physics quarks, or like, yeah, which one stole the name for the other. That's definitely something I haven't found out yet, but I think it's some sort of like it's white. It comes in a jar. I think it might be like the British equivalent of the fluff that Americans put on peanut butter and fluff sandwiches, like marshmallow fluff. It's definitely disgusting, whatever it is, but yeah, yeah. Please comment if you know if you know the answer to that. So the six types of quarks, which are called up, down, charm, strange, top, and bottom. Sometimes these are called truth and beauty, but top and bottom is definitely easy to remember. Um, and this idea of three families of particles is something that there's a theme of. This is going to continue downwards. There's going to be more particles that come in these three families. Um, Up and down are the most common quarks, and you only need up and down quarks to make up protons and neutrons, which are made of three quarks each. These other ones are much heavier and much less stable, and we only see them in these super high energy collider experiments, like Charles mentioned, where yeah, you're really just smashing things together and putting enough energy in that you do get these very short-lived but still identifiable particles. So this is sort of one family of particles, and then we have the leptons. Leptons are lighter than quarks, and whereas quarks make up what I guess I would call nuclear matter. They make up kind of the heavy stuff in atoms, and therefore most of the matter we see around us. Leptons are lighter and faster. This is probably wrong, but I feel like lepto comes from like the Greek for fast or something like that. Maybe someone could correct me on that too. But so the example we all know is the electron. That's a lepton. And there's sort of heavier flavors of the electron called the muon and the tau particle, which again are quite unstable, and we only produce them in these colliders. Muons are a little more stable than the other ones, I think, whereas some of these have lifetimes on the order of like 10 to the negative 8 or 9 seconds or something like that. Really, really very tiny. Muons, I guess I can just Google this. That's kind of the whole point of the screen sharing thing. Muon lifetime. 2.2 microseconds, so 10 to the negative 6 seconds, whereas the top quark lifetime is 10 to the negative 25 seconds. That's real fast. And then the other category, which is the one that my PhD is focusing on, and therefore the one that I'm going to be talking about a lot for the next 4 years. So especially my friends get ready for me talking a lot about neutrinos. Neutrinos are the particles of this diagram that arguably we know the least about. There's one type of neutrino corresponding to each lepton, and they interact sort of in pairs. So one example, the sort of stereotypical interaction that allowed neutrinos to be discovered it's called double beta decay. And what happens is you have a nucleus, which is filled with protons and neutrons, and we pick a radioactive nucleus. So at some point, two of these neutrons that are in the nucleus, some interaction happens, and they both decay into a proton. And this is why it's called double beta decay, because you have this change in the atomic number. Is it the atomic number or the mass number? I think it's the atomic number of the atom changes by 2 during this decay. This is one of the most important processes in nuclear physics. But a common thing in physics is that any kind of process, especially a simple interaction like this one, has to conserve certain properties. So what do we know about neutrons? That they're neutral. So it wouldn't really make sense for two neutral things to become two positive things. Protons are positively charged without something else coming off too to balance that. And it's true, an electron is released by each branch of this decay. And so this sort of, now the sides are balanced in terms of charge. But there's other properties in particle physics that usually get conserved too, besides charge. And in a way, they're all a type of charge. One of them is called the lepton number. So we say that in any given interaction, the number of leptons at the beginning should be the same as the number of leptons at the end. So how many leptons are there at the beginning of this process? Well, neither of these are leptons. These are both hadrons composed of quarks. So there's 0 leptons here, so there better be 0 leptons on the other side. But so far we have 2. The only way around this is for 2 antiparticle leptons to be released as well, because those count negatively as far as the lepton number, and then that brings us back to 0. I probably should have mentioned before, but every particle on this chart has a corresponding antiparticle, which usually has it has the opposite charge, same mass. All of the properties are either the same or reversed, and that's sort of the fingerprint of an antiparticle. What happens in double beta decay is that, well, an electron is released, an anti-neutrino is also released from each side here. I should probably write this bigger. So we have the on each side we have the electron, the proton, and the anti-neutrino, which is of the electron flavor, because these two sort of go together. And then that's just repeated down here. So once people started looking really carefully at this process and realized that if you measure the masses carefully enough of the incoming particles and the outgoing particles, there's a little bit missing, and that there had to be this particle here, which was a lepton. In order to conserve the lepton number, it had to be neutral, because we knew that there were no other charged things coming out. And the only explanation for why we hadn't noticed it up till that point, why it appeared to be so small in comparison to the other particles, was to say that it was massless. So whereas all the other particles on here have some mass to them, they have some bulk, the neutrino was said to be like light in that it was massless. Massless particles always travel at the speed of light, so they're very fast, very difficult to detect, and the fact that it's neutral makes it even more difficult to detect. This was sort of the state of particle physics, as I understand it, up until the 1980s, 1990s, something like that. I have some more comments coming in. I should probably keep up with these more. Oh, thank you, Kai. The quark from physics was stolen from the name for the food. Fascinating. Okay. Gelman was unsure what to name them until he read James Joyce's Finnegan's Wake. This is interesting. I should really have a point system, I think, for giving out points to my best commenters. Let's see. Logan, is the client code already published somewhere? Oh, you're not talking to me. Why are you having conversations about? This isn't about physics. Can I remove Logan from the? Ooh, I can put Logan in a timeout. We're going to put Logan in timeout. Ooh. 300-second timeout. That feels so powerful. I can do that. Let's see. Am I working out Dirac's equation? No, that's going to come later. I will do sort of a QFT review at some point. Yes. So this was sort of the state of the field for a while, because the Standard Model, this whole collection of particles, and this is very much the surface layer. There's a lot more theory that goes into understanding how these particles relate to each other, the different sorts of interactions that are allowed. I'm going to switch back to front-facing camera. The different types of interactions that are allowed, the different parameters that sort of describe, why is this one heavier than this one, why is this one charged and this one isn't. There's a lot of mathematics, and I guess that is sort of the hard math of particle physics that explains why that's the case. And it's this beautiful theory called the Standard Model, which has been essentially perfect in all the predictions it's made, and that's a lot of what particle colliders like those at CERN and Fermilab have worked very hard to confirm, to measure these particle masses to incredible levels of accuracy, and also the rates of interaction between them, and all those numbers line up real well with what the Standard Model predicts. One exception, and I believe it was the first exception to be noticed, was that neutrinos, as it turns out, are not as simple as we once thought. Neutrinos have the possibility, as they're flying through space, and most of them are in space. We observe very high energy neutrinos coming from the sun, coming from very active galaxies further away. There's even some coming from the birth of the universe that have still not been really slowed down or collided with much of anything, and we can still detect those. There's some really cool experiments going on, actually at the South Pole right now, trying to detect those. And that's something UCL is involved with, because UCL particle physics is really cool. Please fund me. So electron neutrinos, for example, we now know can spontaneously change flavor to muon neutrinos. And in fact, all of the different flavors of neutrinos can oscillate between each other with some very tiny rates, but enough that we've been able to measure them. And for theoretical reasons that I definitely don't understand well enough to talk about here yet, this being the case very firmly implies that neutrinos are not massless after all. They have to have some mass. It might be very small, but it's definitely not zero for any of the flavors of neutrinos. And there's a lot of theories. Ooh, I guess I have to switch back to the paper camera for you to actually see that. Yeah, sorry. Electron neutrino, muon neutrino oscillating between each other, and the conclusion that neutrino mass is not zero. This was break in particle physics because it doesn't really fit in well with the other parts of the Standard Model. And there's a lot of competing explanations for it, but because neutrinos are so notoriously difficult to detect, and to detect large quantities of them so that you can really study their properties, we haven't been able to make all that much progress yet in saying which theory about neutrinos is the right one, if any of the ones that we've come up with yet. And we ideally, we don't want to end up with just a theory about neutrinos out of this. This could be a window into a much more meaningful, deeper layer of physics, in the same way that in the early 1900s there were just a few experiments that didn't really fit with what we understood about classical mechanics and classical electrodynamics, and those few kind of weird experiments that most people at the time thought, that's not really important, that's not really something that happens every day, all the stuff with like light diffraction or atomic physics. These aren't things that really show up in everyday life, but that led to the birth of quantum mechanics, which is now absolutely essential for everything from electronics to chemical processes to medicine. Like we would not be anywhere near as well off as we are without quantum mechanics, and this could be a crack that leads to that next great breakthrough in physics. So the still open question of why neutrinos have mass and what are the other properties that neutrinos have, that is essentially the focus of my PhD project, which I'll probably go into more detail at a later date when I understand it better. But the basic summary is that this double beta decay process, which I sort of sketched out before, where 2 neutrons become 2 protons, also releasing 2 electrons, but most importantly, in my opinion, releasing these 2 antineutrinos. If certain properties of neutrinos are the case and not others, it should be possible, very rarely, for this interaction to occur, but without the neutrinos, which would give sort of a different signature and a different distribution of masses and momentums for the outgoing particles. So there's a lot of experiments right now that are dedicated to generating a lot of double beta decays and looking for the ones that don't have the neutrinos. So my project lines up well time-wise with a lot of these experiments really coming online and expanding, and hopefully within the next 3, 4, 5 years it'll be possible to either have identified for sure a neutrino. It's called a neutrinoless double beta decay, or zero nu beta beta, or 0 VBB if you don't like Greek for short. We should either be able to detect one of these pretty soon, or convince ourselves more that they're not possible. And either way, that'll give us some much more valuable information about neutrinos than we have at present. And what I'll be working on is not so much the experimental side, because the experimental side, it seems like they've made a lot of progress and they're really very close, but it's the theory that more needs to catch up in this case. In order to be compared with experiments, we need to have a really good understanding of this particular nuclear decay process, the different interactions that make this make this possible, so that we know when we get this experimental data, does it confirm XYZ theory about neutrinos or not? So I'll be calculating using theoretical techniques and using machine learning techniques the numbers that should be the case according to different models of neutrinos, and also like different extensions of the standard model. What should this interaction look like, so that when the data comes through, a comparison can be made, and hopefully we can draw some pretty interesting conclusions. That is the quick summary. That was pretty quick. I'm gonna check if I have any more comments now. Someone said, "You're massless, Graham." I don't really know what that means, but I'm going to take it as a compliment. I think Logan's mad at me because I timed him out. Charles says, "Admit it, Graham, no one understands their PhD even after they finish it." I from what I hear, that's definitely true, so I'd like to be the exception in this case. Ooh, Logan sent me some private messages, which I don't think I should share on air. I'm gonna call him anyway. We're gonna have our first guest speaker. How should I do this? Okay, if I call... Ooh, this is a technical detail I hadn't considered. If I call him and I have headphones in, I'll be able to hear him, but you won't. But if I call him without the headphones in, I'm gonna get a lot of feedback very quickly. This is a predicament. Anyone have any suggestions on this? Uh, ooh, if I call him on my phone, then I can keep my laptop muted as it is right now, and I shouldn't get feedback. I think, yeah, okay. I'm confident. I'm sort of confident in this now. Calling Logan. For those of you who don't know Logan, Logan is my very good friend from undergrad. We worked on lots of physics together, and now he does very exciting software, which is not even though it's not physics related, it's very exciting. Welcome to the live stream, Logan. The first person to get timed out on my live stream.
Oh, okay. So, sorry, I needed to mute the live stream because it's out of sync.
Oh yeah. Well, I was just talking about that on there. That I think this is the only way I can do it. That it's not gonna create some kind of echo effect. Is there anything you'd like to say to the viewership?
Yeah, what the fuck do you think you're doing? Kicking me out of the chat.
You were breaking.
I was keeping that chat alive.
You were breaking the rules.
There are no rules.
I make the rules.
I didn't read the rules.
No, I didn't actually write any yet.
I'll do my best to answer them. What?
Okay, that's fair. Yeah, but you weren't asking me the questions. You were asking Charles the questions.
I said nothing about that.
Oh, Charles had a suggestion.
Oh.
PC line and cable from phone. Oh, that's smart. I don't have that cable. But you're right. Okay, I need to get that cable. Okay.
Anyway, it's great to be here. This is fantastic. Happy to be on the live stream.
I'm happy you're on the live stream too, and I gotta give Logan some credit because really this whole streaming business was Logan's idea, or motivation at least.
Yeah, you're welcome, everybody.
Thank you. Everybody say thank you, Logan.
I don't remember who thought of it first. I know we were just kind of talking about live streaming.
I remember. Well, I was playing the piano. I was playing the piano in the practice rooms over the summer, and then you called me and you started telling me about how you were gonna live stream some code, and then maybe I was the one who responded and said I should live stream my PhD. So that's how it happened. Yeah, now we know that's how it happened. Do you have any questions about particle physics? That's the lamest question I can think of to ask you.
Sorry, I didn't catch the last thing you said.
I said that's about the lamest question I could have possibly asked you.
Oh, I'll have some questions. I had a bunch of questions, and I was gonna put them in the chat, but I was on timeout for 300 seconds.
Yeah.
And
it's funny how that happens.
Yeah, and so
when
so
you
I
break
forgot
the
all the
rules.
questions.
Maybe they'll come back to you now.
I want to say hi to all the people from Homerton.
I think that's what you're doing right now.
Yeah, hi everyone. Very cool that they are watching your stream. Can I just say hi to everyone?
You're saying hi right now. You're live. I don't know if you knew that.
Hello, Hazem. Is that pronounced correctly? Charles, Ella, Kai. Is it Kai?
Yeah. Very good. Charles again.
Harry. Yeah, Charles again a lot.
Harry's a good guy. Yeah.
Quite a few good comments. He mentions Weston. Arena.
Yeah.
Hi, Arena. I think I talked to Arena.
You
once,
talked to Arena,
a couple
yeah.
times. P. Rob. And Bored to Heck. Shoutouts for everyone. P. Rob said hello to me. He's saying hello to me, I think.
I'm pretty sure. No, I don't know if he is, because that was... No, there's a 30-second delay. I timed it during the testing phase. I don't know if you were around for that. There's an exact 30-second lag.
Oh, bizarre. Okay, so that's probably not to
he's
me.
not saying hi to you. but he might say hi to you soon.
Or maybe he saw me go. Maybe he heard me going down the list saying hello, and he preemptively said hello.
You can choose to believe that if it makes you feel better.
Oh, is P. Rob from UMaine?
Yeah, Phil. Yeah, you know Phil Rob.
I mentioned Yifeng and Bruce.
Because Yifeng and Bruce are awesome, and I hope they're watching this, and I hope they know how awesome they are.
Does P. Rob? Oh, he said it was to me.
Oh, okay, right.
Does P. Rob know who I am? Do I know who P. Rob is?
Well, he said hello to Logan just now. I think that means he might.
I think I'm out of timeout.
Yeah. I untimed out you. Time outed. Is it timed out or time outed? I think it's timed out.
Yeah, I don't know. Oh, Bortek is Gordy. Okay. Well, this is great. We have look at all the people you have in here. This is fantastic.
It's very exciting. Ooh, we had 10 a couple minutes ago, and now we're down to 8. So Logan, now we know that Logan calling makes us drop 20%.
How many people did you have?
I had 10. I had 10 for a little bit.
Oh, we're at 9 now. We just went to 9. That's great.
Yeah, that's good.
I sent out your link to at least one person. Maybe I'll send it to some more.
Yeah, that'd be nice if you want to do that. I feel like I feel like we should talk about. Oh, now we're back up to 10. Because I said something, I guess. What else? What else should I talk about? I was potentially just gonna work on my textbook a little bit, but that seems kind of anticlimactic for the first session. Well, maybe we'll give a little tour through my nice new file system.
Yes, exciting.
So I think, one of the most exciting things that's happened to me in a while was I discovered the WD Linux package. It's very exciting. WD stands for warp directory. So if you're a Linux user, you can use CD to change directory into the directory below you, and using that and then using it sort of like up and down. That's how you move between the folders where all your files are.
Dir? Did you just use dir? Really?
What do you use? ls-l?
LS.
That's lame.
Dir is for Windows users.
I was a Windows user once. Yeah, so the great thing about WD, well, I guess I should go to a different directory so you can see it work. You do WD, and then you can set the name of you can label any directory anywhere in your file system with a particular name. So I can do WD PhD, and it'll bring me right to my PhD folder. It's just like you're setting little flags all around your file system for like the places you visit the most, and I think that's pretty cool. So let's see. So far in my PhD folder, I've got admin, conferences, courses. Let's go to courses. Courses is interesting. So I had a very interesting time, sort of thinking about what courses I wanted to take this term, because the way my program works is it's a mixed program where you're doing primarily a particle physics PhD, but there's also this added data science component which is intended to sort of enrich the PhD and gives access to additional courses and additional industrial projects, and ultimately your project is one that is about physics, but it also has this data science, machine learning element. The name of this is data intensive science, which is sort of one of the new buzzwords in especially physics right now. As sort of, I've read an article where it talked about it as the fourth paradigm of like physics, other than experimental, theoretical, computational physics. That data intensive science is this new realm where you're dealing with experiments and projects that have just massive amounts of data. CERN produces something like, I don't know, it's definitely in the petabytes of data a day, I think. CERN, how much data per day? Let me Google that real quick. October 2017, 12 petabytes of data were written on tape at CERN during that 1 month. Um, and that's only the stuff that gets through their hardware filters. So most of the experiments at CERN, they're reading in all these particle collisions, but the wide majority of them don't really have anything interesting in them. In that, like if we're only looking for certain interactions that are kind of rare, that have some content that we're trying to study, most of the time it may be a very high energy collision with lots of products, but everything in that particular collision is stuff we understand very well, and so it's not really worth holding on to that data. Um, and they have automated systems that get rid of that. So, well, this says it's accessing more than 2 petabytes of data every day. It's probably I would guess on the order of magnitude of 10,000 more than that data being actually generated raw from the detectors, and then they're cutting it down in order to get it to something reasonable that you can actually store and work with. But the point is, there's a lot of data in particle physics, more than in almost any other scientific field, just because of the nature of these experiments. So machine learning tools, big data tools are increasingly important to deal with this all this raw stuff. So, Logan, you're being really loud, and I'm muting you.
Yeah, sorry, me. Wait, hold on. I'll mute my mic instead.
Okay, that's thank you. It sounds like you're like rubbing a cheese grater against the microphone.
Sorry, blue switches. Everyone buy blue switches. MX Cherry Blues.
Yeah.
I'll put a link in the description or in the comments.
I have the power to mute you again. Just saying. Oh, okay. Charles makes a good point. Graham, a hint: most people have trouble quantifying how big even a gigabyte is. So, well, most people probably I feel like megabyte is the most familiar unit to people, because like if you've had a phone for a long time, most the memories of most phones were somewhere in probably the couple hundred megabytes range for a while. I think a typical photograph takes up that's a good question. How many bytes in a photograph? So a typical photograph is on the order of a few megabytes, and a gigabyte is 1,000 megabytes. So that I guess that's why. I guess that's a natural explanation, because we're used to sort of our phones being able to store probably a few thousand photographs in addition to apps and other data. So a terabyte is 1,000 gigabytes. So like 50 iPhones worth of data. Yeah, that's a good unit. iPhones worth of data. A terabyte is like 50 iPhones. A petabyte is 1,000 terabytes. So 50,000 times the entire content of your smartphone is the amount of data that CERN stores from these collisions in just one day, and it's something like 1,000 or 10,000 more than that's being generated and then filtered down. So maybe that gives a little more scale. How did I get on this? Yes, because the course I'm doing has this machine learning component, has this data science component. A lot of the courses that I'll be taking during these first 2 terms, and talking about on these streams, are going to be focused on machine learning and software design. So this term in particular, I'll have one on software development in Python, which I think I'm pretty comfortable with. One on statistical analysis, which is more mathy, but specifically statistics of particle physics, which is a really big deal in particle physics. Understanding, like, not just trying to calculate some number, like you're trying to measure the mass of this particle. You can't just measure the mass. You need to measure the mass and also really carefully understand what the error bars are on that mass, because knowing what those error bars are tell you how accurate your experiment is and sort of how much you can trust it. There's always random fluctuations in experiments. You need to understand the limitations of what you're doing, or you can't really make any credible claims about is it proving this theory or not. So one of my classes will be on that, and then I'll also have a class on more standard particle physics, leading up to more classes next term on specifically machine learning and data science. But anyone who knows me knows that I like to overload on courses if I have the freedom to do so, and I do have the freedom to do so right now. And let's see. I guess the best the best way I can exhibit this is to show the documents I made. So I went through UCL has this timetable of all their math and physics courses, and it's set up in such a way that you can sort of select the ones you're interested in and generate a sample, like what your schedule would be like. So this was all the math courses I came up with. Just I think the word is too many. Definitely too many. But these are all topics I'm interested in, so like it's difficult to choose between them. Out of all of these, the ones that are realistically actually relevant to what I'm doing are representation theory, which is the study of how algebraic structures, which is kind of an abstract thing to explain. I should probably set aside a whole separate stream for like math topics, but it's to do with symmetry. The physical application is symmetries that physical systems can have, and in particle physics, symmetries are super important for understanding the differences between different particles. A lot of these geometric courses could also be interesting. Unfortunately, the timings on a lot of these didn't work out. But the one that did work out that I'm pretty excited about is graph theory and combinatorics, because graph theory is really cool, and it sits right at the interface of both math and particle physics, because in particle physics we use Feynman diagrams, which are sort of I think pretty like pop science, well known, as a visual way of expressing different equations. Like when you have some particle interaction, the nature of quantum physics and particle physics is that it's never just that one interaction happening. So when I drew, switch back to paper. When I drew that process before of the two, well, I'll just do one of the neutrons becoming a proton, and an electron comes out, and a neutrino comes out, antineutrino. This process is the first order process, because this is sort of the bare minimum that needs to happen to have this incoming product become these three outgoing products. But in reality, that's never just what's happening. I'm definitely not an expert on the physics of this particular interaction, but to be very vague about it, say a neutron is going along, it's possible for some other particle, like say a photon, to get emitted from it and reabsorbed. This is something that can happen. And maybe this happens before it becomes a proton. And sometime, I'm definitely doing a bad job explaining this. This is wrong. This is bad physics, but hopefully a good general explanation. It might be possible for this photon to emit an electron, and and this somehow becomes a proton along the way through, and then maybe the neutrino gets released somewhere in here as well. And here we have a fundamentally different interaction than this one, but it has the same inputs and the same outputs. So because this is all happening way too tiny for us to really zoom in on, all the different processes like this that have the same input and the same outputs are indistinguishable for us, and they all get added together. And the idea of Feynman diagrams is that if you want to calculate something like the probability of this interaction happening, you have to sum together all the possible diagrams that are allowed by whatever the rules of the physics are. So this one's probably not allowed because I just made this up, but there's always some infinite set of possible diagrams with more and more complicated bubbles going on, and you add together. If you add together all of them to infinity, you get the exact answer, but that's not really computationally possible in most cases, and so you end up just adding together either a very simple calculation would be just calculate this one. That's called leading order. Leading order, you don't worry about any extra processes that might be going on. You calculate this particular interaction and you get a number and you call it good enough. The next layer would be next to leading order, where you allow one layer of complications to happen. So there could be one extra loop in here, or one extra particle getting emitted and reabsorbed, and you add all those in, and you get corrections from the leading order to the next to leading order. But the more complicated the interaction, next to leading order could mean adding in maybe dozens, if not way more than that, of possible interactions. And by the time you get to next to leading order, you could be talking. You get to the point of calculating all of these may or may not be feasible within the scope of an actual experiment, and we've only gone a couple layers in. So graph theory is loosely connected to this because these are graphs. A graph is anything where you're studying sort of pathways and connections between different objects, and there's a lot of really cool mathematics linked to that applies to. If you know graph theory, you can apply it to any graph. So I'm hoping that by understanding that better, I'll be able to understand this side of particle physics better too. And the other thing that it applies to is which I'm definitely not going to get into tonight because I'm getting pretty tired. But machine learning, in many ways, is also a type of graph. It's a network. Machine learning tools rely on a lot of machine learning tools like neural nets rely on sort of simulating the human brain. They sort of abuse the structure of neurons in a very simplified way to say, okay, I have all these data inputs, and I'm going to tie all these data streams together to neurons with different, and those neurons have different strengths and different properties to them. If you've done any biology, you know that neurons they sort of fire when they get enough potential from their different inputs. So this is all written in software. This isn't a physical thing like in the brain. But by having different layers of these neurons and different interconnections between them, you end up with a modeling device that all these parameters that control how strong the neurons are, how they interact with each other, can get optimized so that whatever this particular problem is you're trying to solve. Like the stereotypical example is taking pictures of people's handwriting, like of a number, and outputting like in a digital form that number from the list of all possible numbers. So that particular prediction, in order to do that accurately, there's some set of weights and labels on these neurons that is optimal and leads to the best predictions. And finding that is sort of the task of basic machine learning. But once again, this is connections between nodes. It's not mathematically. This isn't all that different from this. It's graph theory. And so that's one course that I'm pretty excited about sitting in on this semester. Actually, I've got my first course tomorrow, so I'll probably give an update on how that goes. I checking for any more questions. I think I'm gonna cut it off pretty soon for the night. It's 12:18 London time, and I do have class at, I forget what time. Pretty early tomorrow, so I should probably go to sleep. But thank you to everybody that tuned in, and this is definitely not going to be a one-time thing. So if you're interested, please toss me a subscribe, and I'll be certainly bugging you all real soon on Facebook and other places to as I continue to change and improve and evolve this format. But I think certainly the next time I do a session will be sometime within the next couple days, and I'll make it more of a working session where I'll be either reading a paper or working on part of a course and kind of working out loud as I do so. And as always, open for questions. Yeah, I think that's it for now. Thanks again for. I'll switch it back to. I really need a keyboard shortcut to switch between the front-facing camera. Yeah, so thank you everybody. Have a good night. Bye.
Bye, friends.
Yeah, Logan also says bye.